What if I told you that trying to make a computer program perfectly organized, like perfectly structured, is often the exact thing that makes it completely impossible to read?
It sounds totally backwards, right?
Right.
I mean, we're so conditioned to think that more structure just automatically equals more clarity.
Right. When you first look at the concept of a complex piece of software, you expect it to read like a well-oiled machine.
Yeah, exactly.
You imagine opening up the source code for, say, a modern banking system, and you think it's going to look like a simple instruction manual. Do this, then do that.
But anyone who has actually peeked under the hood of enterprise software knows that is definitely not what happens.
No, not at all. Instead of a manual, you find yourself staring at what looks like a foreign language, and
Mm.
it's like you're trying to read it in the dark.
And just to make it a little more chaotic, the pages keep rearranging themselves while you're trying to read them.
Well, yeah.
It really can feel like total architectural chaos, especially if you are just starting out.
Well, if you've ever felt like learning to code, or even just trying to understand how the digital world is designed, is this insurmountable task, you are in the right place. Welcome to today's deep dive.
Glad to be here. We got some fascinating stuff to unpack.
We really do. Today, we are turning the lights on. We are stripping away the jargon and looking at the foundational architecture of the systems that run our daily lives.
Which is so needed.
Right. We're diving into the paradigm of object-oriented programming, or OOP, and we are going to extract the core pillars of how software is actually built. We want to translate all of that into plain, simple concepts for you.
And that's incredibly important because object orientation has been the dominant paradigm for, what, decades now? But the way it's traditionally taught often completely obscures the actual brilliant logic behind it.
Yeah, it gets lost in the weeds.
Exactly. To build a sustainable system, really any system, whether it's a bridge or a mobile app, you first need to deeply understand the raw materials you're building with.
So let's start with the absolute bedrock. The foundational material of software design is something called abstraction, specifically data abstraction.
Right.
And from what I understand, this is fundamentally about drawing a very strict boundary between two things, the what and the how.
You hit the nail on the head. And to understand why this boundary is so revolutionary, we really have to look back at the origins. Think about a pioneer like Barbara Liskov.
Oh, back in the 70s, right?
Yeah, back in the 1970s at MIT. At the time, programming was often seen as this highly mechanical, hardware-focused task.
Like just flipping switches.
Basically,
Yeah.
you were flipping switches and managing the actual physical memory of a machine. But Liskov approached it completely differently. She saw programming not just as a mechanical problem, but as a mathematical one.
Which is a huge shift in perspective.
Massive. She argued it should be guided by logical principles and, honestly, aesthetic beauty.
It's funny, I think people rarely associate computer code with aesthetic beauty, but when you see it done right, it really is elegant.
It's highly elegant. I mean, she led the creation of a language called CLU, which gave us the concept of the abstract data type, or ADT.
Okay, ADT.
The core philosophy here is that you define a set of values and the operations you can perform on them, completely independent of how the computer actually executes them behind the scenes.
So it becomes an axiomatic mathematical structure.
Exactly.
Let's ground that a bit, though, because axiomatic mathematical structure is exactly the kind of phrase that makes a beginner's eyes just totally glaze over.
Fair point. Fair point.
Think about something incredibly basic like the number 2. When you use an integer in a program, you know how to add 2 and 3 together. We take that ability entirely for granted.
We really do.
But as an ordinary user, or even an ordinary programmer, you have absolutely zero knowledge about the computer's internal bit pattern representation. You don't know how the silicon is actually storing those ones and zeros in its physical memory to represent the number 2.
And you shouldn't have to know. If you had to understand the electrical engineering of a microchip just to add 2 and 3, I mean, you would never be able to write a complex program.
So abstraction is really just like driving a car.
Oh, that's a good way to put it.
Right, like I know how to use the steering wheel and the gas pedal. That is my interface. That is the what. If I press the gas, the car goes forward. But I don't need to understand the complex thermodynamics or the fuel injection chemistry happening inside the engine block just to get to the grocery store.
Exactly. That chemistry is the how.
Yeah.
The automotive engineers decide how the engine works based on the physical constraints of the car. You just press the pedal. And that strict separation, that is the magic of data abstraction.
It protects you from information overload.
It does. And crucially, It allows the engineers to completely swap out the engine, maybe upgrade it from gas to electric, without you having to relearn how to drive. You still just press the pedal.
Okay, so abstraction isolates a single concept, like our car. But a complex software program isn't just one isolated car, it's a whole city. It's fleets of vehicles.
Uh-huh.
How do we manage the relationships between all these isolated objects without rewriting the rules from scratch every single time?
Well, that introduces the second core pillar, inheritance.
Inheritance.
Yeah. Inheritance is the mechanism for taking an existing concept and extending it to create something more elaborated, something with additional properties.
A great way to visualize this from the source material is the concept of a stream of data.
Right. Imagine you have an information stream, a file stream, and a network stream.
Yeah,
They're all slightly different based on where the data is coming from.
right.
But fundamentally, they share common universal operations. Regardless of the source, you might need to map that data, sort it, or filter it.
So instead of writing the complex logic for like how to sort data 3 completely separate times, once for the file, once for the network, and once for general information, you put that sorting logic in one central generic base class.
Exactly. You create a base class that knows how to do those common operations.
Uh-huh.
Then, your specific streams, the file stream or the network stream, become subclasses.
And they just inherit those abilities.
Yep, they inherit those sorting abilities automatically, but they still handle their own highly specific nitty-gritty storage details.
I mean, it sounds incredibly efficient. You write the code once, and everything downstream gets to use it.
It is efficient, but...
But here is where we run into a massive trap.
Oh, yeah.
This is where that idea of more structure means better code completely falls apart, because developers often get so intoxicated by objects and inheritance that they over-engineer things to the point of absolute absurdity.
It's so true. The practice of object-oriented programming varies wildly in the real world. More objects do not automatically mean better software. In fact, it often means the exact opposite.
Let's look at a classic, almost comical trap. Imagine you are writing code to calculate a simple bank balance with interest. The clean, basic way to write this is just a mathematical statement. It just reads, balance equals balance times 1.0 plus interest rate.
Anyone reading that, even a non-programmer, can look at the multiplication sign and generally intuitively guess what is happening. It's clear, it's direct, it's unambiguous.
But then you encounter the object-rich version. Someone decides that every single number needs to be an object and every action needs to be a method hidden inside those objects.
Oh, no.
Yeah. So that simple math equation turns into this monstrous line of code. It reads balance.add, open parenthesis, balance.get, open and close parenthesis, dot times, open parenthesis, interest rate, close parenthesis, close parenthesis.
Wow. Hearing it read aloud really highlights the mental gymnastics required to understand it.
It's a complete nightmare to read. My brain has to parse 3 different nested commands, jump inside parentheses, and reverse engineer the logic just to realize we are multiplying 2 numbers.
Yeah, it completely defeats the entire purpose of abstraction.
Exactly. Instead of hiding the complexity, this approach unnecessarily introduces software complexity. If I am a developer trying to fix a bug in that code 2 years later, I am going to have a massive headache.
And that reality forces us to ask a critical question. If object-oriented programming is supposed to improve software maintainability, but it's this easy to create unreadable, fragile code, how do we actually connect these components safely?
Right. We have these beautiful abstractions, but objects don't just sit in a vacuum.
No, they have to interact. They have to make decisions based on user input.
Which introduces a whole new level of risk, because building software isn't just about defining things, it's about dictating the flow of logic.
And the most common way beginners manage the flow of logic is through static conditionals. You know, the classic if-else statement.
Right.
If condition A is true, do this. Else, if condition B is true, do that.
Which makes sense intuitively. It's how we make decisions in real life. If it's raining, take an umbrella. Else, wear sunglasses. But relying on multi-conditional statements sitting right in the middle of your high-level business logic is a major vulnerability.
Think about the structure of a standard block of business logic. You might see something like, if command equals choice A, do this. Else, if command equals choice B, do that. Else, do something else. The fatal flaw here is rigidity.
Because software requirements are never static, the business team is always going to come down the hall and ask for a new feature.
Always. Every single time. So what happens when the business needs choice C and choice D added to the system?
Well, I have to go find that exact critical file. I have to crack open the core business logic that handles everything, type in more else-if statements, and hope that while I'm in there, I don't accidentally delete a semicolon or mess up a bracket that brings the entire server down.
Yeah, it's terrifying. Every modification is a roll of the dice. This is highly fragile architecture. And this is exactly where we introduce a much more sustainable solution, flexible polymorphism.
Polymorphism. It's an intimidating word for sure, but it just translates to many forms.
Right. In practice, polymorphism is a way to defer the decision of what to do until the very last millisecond when the program is actually running.
Okay.
Instead of a giant, rigid list of conditionals, you use an interface. Let's call our interface iDoer.
iDoer, a thing that does something.
Yes. And you pair that interface with a service class. We call this an object factory or a doer factory.
So instead of that massive, terrifying if-else block, the new code is incredibly brief. It just looks like this iDoer doer equals doerFactory.makeDoer based on the condition. Then doer.do something.
Look at how clean that is.
Yeah.
The main business logic doesn't care about choices A, B, or C anymore. It just says, hey, factory, look at this condition and give me the correct worker. I don't care who it is. I'm just going to tell them to do their job.
Okay, I see how clean it looks, but I really have to push back here.
Sure, go for it.
Because logically, those if-else statements still have to exist somewhere, right? The factory has to figure out which worker to hand over.
Yeah.
Haven't we just swept the dirt under a different rug? How does moving the mess actually fix the fragility of the system?
You absolutely swept the dirt under a rug. The conditionals are simply moved into the doer factory's make-doer method, but here is the critical difference. It's about where that rug is placed.
Oh, I see.
This is a deliberate, highly calculated trade-off. We are trading a slightly more complex and perhaps marginally less efficient code structure for long-term sustainability.
So we are protecting the important parts of the house.
Exactly. By isolating that messy conditional logic inside a factory, your high-level business code, the main floor of your house, the brain of your application, remains completely stable and untouched.
That makes sense.
When a new process is added, you don't touch that core file at all. You write a brand new, entirely separate class that implements the iDoer interface. Then you quietly update the factory in the background to recognize it. The factory dispatches the new class just in time.
It's kind of like a restaurant.
Okay, let's hear it.
If I am the customer representing the high-level business logic, I just want my chicken. I don't want to walk into a chaotic kitchen, dodge 20 different chefs, look at a giant list of responsibilities, and figure out who is cooking the poultry today.
Right?
The waiter is the factory. I give the waiter my condition. I want chicken. The waiter navigates the messy kitchen, finds the right chef, and brings me the food. My dining experience is perfectly clean and stable, even if the kitchen is constantly hiring new chefs.
That is a perfect analogy. The factory acts as a wall, hiding the volatile implementation details from the stable business rules.
So if you are staring at a blank screen, trying to build a sustainable system from scratch, how do you actually apply this? What is the blueprint for an extendable system?
Well, the process starts by zooming all the way out. The very first move isn't writing code at all. It's looking at the software requirements and designing your data abstractions first. You design your interfaces.
Right. These interfaces act as conceptual virtual machines.
That's a great way to think about it. An interface is like a contract, an airtight box that promises certain inputs and outputs without defining how the work is actually done inside the box. You are establishing the borders of your system.
Getting the rules down.
Exactly. You ensure the high-level business logic is set in stone before you worry about anything else.
And then comes the hardest part for an eager programmer waiting.
Oh, yeah?
You actively delay the decisions on the implementation details. You build the architectural structure of the house before you pick out the drapes. You allow the concrete classes, the actual code that does the math or saves the data, to evolve and mature much later in the process.
And finally, you bring in those object factories we just discussed. You hide those messy implementation details behind the factory walls, so the system can dispatch different behaviors dynamically without breaking the core logic.
Implementations depend on abstractions, not the other way around.
You've got it.
But as you design this system, you inevitably face a major architectural choice. We talked earlier about inheritance, that family tree where a file stream inherits from a base stream.
Right.
If inheritance lets me reuse code so easily, shouldn't I just build massive, deep family trees for everything? I could have an animal base class, a mammal subclass, a dog subclass, and a golden retriever subclass. Shouldn't I just inherit everything to save time?
The empirical evidence in software engineering heavily suggests you should avoid doing exactly that.
Wait, really? Why is deep inheritance so dangerous?
Because deep code inheritance, where you have layers upon layers of actual working code rooted together, adds massive rigidity. Stick to your animal family tree.
Okay.
If you realize later that your base animal class needs a new feature, say the ability to breathe underwater,
Yeah.
and you change that root class, that single change cascades instantly. It affects every single branch above it.
Oh, wow. It's a house of cards. A developer tries to fix a tiny bug in the login screen, and because it shares a deep root object with the e-commerce system, they accidentally cause the checkout cart to delete everyone's credit card data. The system becomes completely unpredictable.
Program verifiability becomes almost impossible at that point. If a change near the base breaks a class 20 layers away, you just can't trust your own code.
So if we shouldn't use deep family trees, what is the logical alternative? How do we organize things?
You rely on interface inheritance instead. This means your hierarchies should be extremely shallow, just 2 or 3 layers deep.
Just keeping it flat.
Yeah. And more importantly, they shouldn't be about sharing huge blocks of code. They should be focused entirely on creating replaceable objects with polymorphic behavior. You share the what, not the how.
Keep the contracts, drop the shared mechanics.
Exactly. And beyond that, if you have a class that only contains static operations, meaning it doesn't need to hold on to any internal state or memory, it just does a calculation and returns an answer. It shouldn't be treated as an object at all. Yeah, it doesn't need to be part of an inheritance tree. It should just be a classic traditional module.
So keep it simple, use the right tool for the job. Inheritance generally doesn't compete favorably on code reuse when compared to simple, independent modules.
Not at all.
The potential harm of a deep family tree often drastically outweighs the benefits.
It is a massive paradigm shift from how basic programming is sometimes taught. You are no longer just writing sequential lines of code. You are designing, interacting, self-sufficient, but safely isolated computing machines.
Let's step back and look at the journey we've taken through this dark room today.
Sure.
For everyone listening, you now have a fundamental understanding of how software architects think. You know why Liskov's data abstraction, separating the what from the how, is the absolute bedrock of modern computing.
Essential stuff.
You know why that balance.add code is a nightmare of over-engineering? And why object factories, despite just acting like a waiter moving the mess around, actually protect your system from catastrophic failure? And you know why keeping your family trees incredibly shallow prevents the house of cards from collapsing.
The principles of managing complexity will always remain the same. Isolate the volatile parts of your system away from the stable parts.
But we can't end this deep dive without acknowledging a major shift happening right now. Because the strict boundaries of object-oriented programming that we just spent all this time defining, they are beginning to dissolve.
They really are. The software landscape is constantly evolving. Newer languages like Go or the modern evolution of JavaScript are actively blurring the lines between strict objects and traditional functional programming.
We are seeing the rise of things like lambda expressions, which sounds like science fiction, I know, but it essentially means treating a piece of behavior, a function, just like a piece of data.
Right.
Normally, an object is a thing that has behaviors attached to it, but what if you could just pass the behavior itself around? Like handing someone the action of running without needing to attach it to a runner?
When you can pass behaviors around dynamically like that, the need for rigid, deep inheritance trees becomes even less relevant. We're moving toward a paradigm-neutral ecosystem.
A mix and match approach.
Exactly. Developers are mixing and matching objects and functions based purely on what solves the problem best, without strict adherence to one dogma.
Which leaves us with a final, provocative thought. If modern software development is rapidly moving toward an ecosystem where these strict categories completely dissolve, how might the very definition of an object change in the systems that will run our world 10 years from now?
It's fascinating to think about. If we aren't bound by rigid structures, the software of the future might look entirely alien to a traditional OOP developer today. The grammar of the language is shifting.
It really makes you wonder what the code of the next decade will look like. You might not speak the whole language fluently yet, but now at least you understand the architecture of the grammar. Thank you for taking this deep dive with us.